All right, hi folks, this is Larry Mussolino recording a video for Module 3 homework. This is Chapter 6. I also posted a video on Chapter 5, so this is a second video on Chapter 6. This has to do with discrete distributions. So let's take a look at this first one. It says, suppose the probability of a customer purchasing 0, 1, or 2 books is 0.2, 0.3, and 0.5 respectively. What's the expected number of books? Well, expected number is really the same as average or mean. Well, the way you calculate a mean in this example is you add up all of the sums of the value of the random variable x times its probability. Let me show you what I mean by this. I'm going to make up a little table. You could purchase 0 or 1 or 2 books. We call this x the value of the random variable. And let me write down the associated probability. In our example, they're telling us 0.2, 0.3, and 0.5. I'm going to multiply these rows straight across. So I'm going to take x times its probability. So for the first row, it's going to be 0 times 0.2. Well, that's just 0. Second row, it's going to be 1 times 0.3. That's 0.3. Third row is 2 times 0.5. That's 1. So we just calculated x times its probability for each row. Now we just add up these numbers. So I'm going to add these numbers up, and I'm getting 1.3. So that's the mean or expected value here. So the answer is 1.3. What it says is over the long run, we expect someone to purchase about 1.3 books. Now, of course, you can't purchase 1.3 books, but we know this is like a calculated average. In the same way, the federal government might say the average family has 2.4 kids. Well, we know no family has 2.4 kids, but they have between 2 and 3 kids. All right, let's go ahead and do another example like this. Here's number 2. So again, I'm going to go ahead and make up a little table with this data. So that says, let's read it over here. It says a marketing agency has developed 3 vacation packages. They estimate 40% of customers will choose the day plan, which does not include overnight. 50% will choose overnight, which is 1 night, and 10% will choose the weekend plan. So let's make up a little table here just so we can kind of organize this. So there's the day plan. Then there's the overnight plan. The overnight plan. And then there's the weekend plan. All right, and really what we're interested in here is how many nights, right? It says find the expected value of the number of nights customers will need. So let me make a little column here for number of nights. Well, for the day plan, there's no nights included in that. Overnight plan is 1 night, weekend plan 2 nights. And now let me write down the probabilities. They told me 0.4 for the first row, 0.5 for the second row, and 0.1 for the third row. Well, I'm going to think of number of nights as x, the value of the random variable. So let's go ahead and calculate the mean. You add up the multiplications of x times its probability. By the way, we usually use the Greek letter sigma to indicate add up. So we're going to add up x times its probability. So let me make a new column here. I'm going to take the number of nights times the probability. For the first row, it's going to be 0. For the second row, it's going to be 0.5. For the third row, it's going to be 0.2. All right, I'm just going to add these up. I'm getting 0.7 as the mean. So on average, customers are going to be selecting 0.7 nights. Of course, it's not possible to select 0.7, but we know it means that customers are going to be selecting between 0 and 1 nights. All right, let's go to part B of the question. Now that we know the mean is 0.7, they're asking us to find the standard deviation. Well, what we're going to do first is find the variance, because once we find the variance, the standard deviation is the square root of the variance. So let's find the variance first. That's a little easier. Well, there's a formula that says if you want to know the variance, you take the sum of x minus the mean squared times the probability. So let me make up a little table again. X was the number of nights. That was 0, 1, and 2. The mean we know is 0.7. So I'm going to calculate here x minus the mean. That's going to be 0 minus 0.7. That's negative 0.7. Second row is going to be 1 minus 0.7. That's 0.3. And the third row is going to be 2 minus 0.7. That's 1. All right, but we need x minus the mean squared. So I'm going to work out x minus the mean squared. All right, this is going to be negative 0.7 squared. That's 0.49. Second row is 0.3 squared. That's 0.09. And the third row is 1.3 squared. That is 1.69. All right, we need one more column because we have to take x minus the mean squared times the probability. I'm going to write the probability back here in this first column. It was 0.4, 0.5, and 0.1. All right, so let's go ahead and fill in this last column. So we're going to take 0.49 times its probability, which is 0.4. So if I work that out, I'm getting 0.196. Let me go to the second row. X minus the mean squared, that's 0.09, times its probability of 0.5. That's 0.045. And this bottom one is x minus the mean squared, that's 1.69, times its probability 0.1. That's going to be 0.169. All right, so we have these, we have this last column calculated. Well, the variance is summing up. So I'm going to add these numbers up. So I'm going to add these up. The sum here, if I add this up, works out to be 0.41. But remember, what we just calculated is the variance. This problem is asking us for the standard deviation. Well, the standard deviation, that's that Greek letter sigma, is the square root of the variance. So this is going to be the square root of 0.41. If you work that out on your calculator, it works out to be 0.64. Remember, the standard deviation is measuring how spread out the data is. All right. So that one's a little messy, but let's go to number 3. All right, it says here, a company selling glass ornaments expects 12% will break in shipping. You purchase 2 ornaments and have them shipped separately. What's the probability both arrive separately? Well, what I got to take into account here, if there's a probability of 12% breaking, that must mean there's an 88% chance of the ornament arriving safely. And they're asking me to find the probability that item 1 arrives safely and item 2 arrives safely. Well, the probability rule, when the events are independent, and by the way, that's part B, the events are independent. The reason is these 2 items are getting shipped completely different, right, to different addresses. And so what happens with one shipment in no way affects the probability of breakage for the other shipment, right? It's like the 2 shipments are completely separate and independent. Well, this formula that says if you want to know the probability of 2 events happening when they're independent, you take the probability for item 1 and multiply it times the probability for item 2. Well, in this example, we want to know the probability they both arrive safely. So this is going to be 0.88 for item 1 times 0.88 for item 2. And if you work this out on your calculator, you get the answer 0.77. So I had to recognize here that they wanted the probability of both items arriving safely. The way you can figure that is take the probability that one arrives safely times the probability the other arrives safely. That's valid when the two events are independent. All right. Folks, let's take a look at this one. It says in an airport entry site, a computer is used to randomly decide whether they should open a bag for inspection. Let's say the chance of being selected is 14%. Can you model your chance of having your baggage open using a Bernoulli model? Well, of course, we have to know, what do they mean when they say Bernoulli model? Well, there's 3 conditions. First, there has to be only 2 possible outcomes for each trial or each experiment. Usually we think of it as like success and failure. You know, it's kind of like flipping a coin or answering a true-false question. The probability of success is the same for each trial, and the trials are independent. Well, let's see if all of these conditions are met. It says here, is the act of inspecting a bag, is there only 2 possible outcomes? Yeah, because you're either going to open the bag or not open the bag, right? You're either going to inspect it or not. So there's really only 2 outcomes here. So the answer to that one is yes. Is the probability of success the same on every trial? Yeah, they're telling us assume the probability of success is 14%. So every time a bag goes through this inspection point, there's a 14% chance it gets selected. So yeah. Are the trials independent? Yes, they're independent, because what happens with one bag in no way affects what happens with the next bag, right? Every bag goes through the same inspection evaluation. So all 3 of these conditions are met. So yes, we can model this using a Bernoulli model. All right, so all the conditions were met here. Okay. All right, let's take a look at this one. It says you have arranged interviews at 4 companies. Each company will either ask you to come to their site for a follow-up or not. Let X be the random variable, the total number of follow-ups you get. Remember, you're going to interview at 4 companies. What are all the possible values for this random variable X? Well, maybe none of the companies call you for a follow-up. That would mean X equals 0. Maybe only 1 company calls you. Maybe 2 companies call you, 3 companies call you. Maybe all 4 companies call you. That would be your lucky day. Well, this is the only possible results for X. So those are the different values of random variable. Now, when these values can only take on certain numbers like this, we call it discrete. So this is going to be discrete. Okay. Is this a uniform? Do you think a uniform distribution is appropriate? Well, uniform distribution means it's equally likely. Well, these are not equally likely if you think about it. You know, it's probably pretty unlikely that 4 companies all call you back. It's probably more likely that maybe you get a call from 1 company to come in for a follow-up. Right, so these are all not equally likely. So we would say, no, a uniform distribution is not a good way to model this. All right, let's take a look at this one. So it says here, a company's database includes data on whether the employee has a dependent child. Is this discrete or continuous? Well, really, this is going to be a yes/no answer, right? Either it has a dependent child or not. You can almost think of it as like a 0 or a 1. Well, it's going to be discrete because it can only take on certain values. A continuous variable is one that can take on any value. Let me give you an example. How about if I'm weighing apples? Well, the weight of apples is continuous because when I weigh some apples, it could be 2.71493824 pounds. This weight can take on any number. Okay. How about this one says compensation? Well, compensation is continuous because it can take on any value, any compensation value in the compensation range of the company. Right? It can range from, a low number to a very high number. Okay. All right. This one I think we just did about a baggage. So this looks like a repeat question. So we'll skip that one. How about this one? It says, at many airports, a traveler entering the U.S. is sent randomly to one of several stations where passport is checked. Each one of 23 stations is equally likely. Can a uniform model be used here? Well, a uniform model is where it's equally likely. So imagine there's 23 stations for you to go to. Well, it's equally likely that you can go to any one of those 23. So yes, a uniform probability model is appropriate in this example. All right, let's take a look at this one. This one's a little tricky. It says, a study shows that 27% of all firms are owned by women. You call 3 firms. What's the probability that all are owned by women? Well, there's a couple of ways I could set this up, but one way I can think about this is that because they're asking me for all 3 women, the probability that all 3 companies are owned by women, I can really think of it this way. This probability is the probability that the first company is owned by a woman, and the second company is owned by a woman, and the third company is owned by a woman. And I think we can assume that these events are independent, meaning, there's no relationship between these companies. So what happens with the first company doesn't affect the probability for the second company. Well, when you have an and probability like this, if you remember, you're allowed to multiply these probabilities together. Well, we know the probabilities for each one of these. The probability that the first company is owned by a woman is this 0.27. Probability of the second company owned by a woman, same thing, 0.27. And the same thing for the third. And if I multiply these all out, I get 0.020. So again, when you're finding the and, or the the probability that all these events are going to happen together, you can multiply the probabilities together as long as you can assume that the events are independent of one another. All right, folks, hope this is helpful as you're working in the Module 6 homework.